Welcome back, Algebra. We are in Chapter 4, Section 6, direct variation. So we're moving from slope y-intercept form to direct variation, yet another linear form. Direct variation actually is so easy it's hard sometimes. It looks like y equals a times x. So notice the slope, which we usually use the letter m to represent slope, right, has become a. And notice there's no addition of b. So if we were going to add something, what could we add? Plus 0, that's right. So a may not equal 0. If a equals 0, it eliminates the variation that we see when we input x. So a now is the constant of variation. It's still the slope, but because it is the only thing constant about this equation, the only non-changing term in this equation, it is known as the constant of variation. You know, and in some other textbook series, that letter is often K, which kind of sounds like the same sound that constant makes. But anyway, you might see a different letter if you're working in a different textbook. So, once again, if we think about our slope-intercept form, the y-intercept is not seen in this equation, so it's really 0. So we always have a y-intercept of 0. And then we can see what's left is y equals mx, or we can call it y equals ax in this case, right? So the first thing you might be asked is, when you look at an equation, is it a direct variation equation? Does the equation represent direct variation? If yes, identify the constant. Once again, the constant is the slope, or in this model, it's the letter A. Okay? So let's see. In this equation here, we see an equation in standard form. So in order to determine whether it's in direct variation, a direct variation equation, let's isolate y, right? Let's solve this equation for y. Okay, and so what do we want to move first? That's right. Let's move the x term away. Let's subtract it from both sides of the equal sign. And we now have negative 4x on the right. On the left, we have 5y. And to finish, what do? That's right, we divide both sides by 5. And we have y equals negative 4/5 x. All right. Now, is this direct variation? Well, it is an equation that does look like this model, doesn't it? We don't see any plus a constant. So if we were going to put something there, we would put plus 0, right? 0. So what would the constant... So we can say, yes, this is direct variation. And then the constant of variation, we'll call A equals negative 4/5, which again looks like the slope, and it is the slope. So go ahead and pause and try this one. Okay, if you're back, I hope you isolated y. Once again, an easy way to isolate y might be to add y to both sides. 2x equals y plus 3. And then just subtract 3 from both sides. Y equals 2x minus 3. Now remember, we can just pick up an equation and take a turn to the other side, can't we? So we can move the y to the left side. Y equals 2x minus 3. There you go. Now, is this direct variation? Well, I see a y-intercept at negative 3. So, not direct variation. We could identify a slope here, right? What is the slope? That's right, it's 2. But the y-intercept is at negative 3, so this is not direct variation. Okay, go ahead and try it with these. Are these direct variation? If they are, please state the constant of variation. Come back when you're ready to check them. Okay, in number 1, we just add x to both sides. And we find that y equals x plus 1. Uh-oh, we've got a y-intercept at 1, so not direct variation. Number 2, if we subtract 2x from both sides of the equal sign, y equals negative 2x. Yes, this is direct variation, and the constant is negative 2. And finally, in this case, we might want to, let's do what you probably did, which is subtract 4x from both sides of the equal sign, right? Negative 5y equals negative 4x, and after you divide by negative 5, y equals 4/5 x. Is this direct variation? Yes. Direct variation, and the constant of variation is 4/5. All right. So let's look at some direct variation graphs. As I've already said, direct variation graphs all have y-intercepts of, say it, that's right, 0. Or that is also known as the point of origin, isn't it? So when we look at this equation, is this direct variation? Yes. I see y equals slope times x, ax. If we were looking this in slope-intercept form, y equals mx plus, what you don't see is the y-intercept. We can add it in, plus 0. You may do that to any direct variation equation, right? So if we're going to use this slope-intercept form to graph, we can go plot the point we know. And what point do we know? That's right, the y-intercept. It's at 0. There's our x, there's our y. Each blue line represents 1 unit on this graph. Okay, so from this known point is 0, 0, the point of origin. We can use our slope, right? Slope, or the constant of variation, is up 2, rise 2, and run 5. So there's the second point. Okay, remember we could also go down 2 if we go to the left 5, right? These two are equal. Down 2, 1, 2, 3, 4, 5, to the left 5. So there we have 3 points, and we carefully grab a ruler. I'm going to try to freehand this and draw your straight line. Very good. One quick note, when we look at this, is this slope a positive or negative slope? Yeah, it's positive. So does this line look positive or negative? Well, remember, when our little ant crawls left to right, it's going up, a positive slope. So that is reasonable. It makes sense. And this 2/5 is kind of flat. And when we have a fraction that's less than 1 like that, we'll have a flat type of slope. So very good. Go ahead and pause and graph this and come back and check your work. Okay, once again, if we put this into slope-intercept form, we could add what you don't see in that equation, and that is 0, right? So slope is negative 1/2, and the y-intercept is at 0, as all direct variations are. So we plot the y-intercept, and now we use our slope. Remember, that's rise over run, right? So from our point, we go down 1 and to the right 2. We also could go up 1 if we go to the left 2. That's also equal to negative 1/2, isn't it? These are all equal, okay? And so there you go. You could continue to make points, and ultimately we need to draw the line for this direct variation. Awesome. Now let's see if you can write a direct variation equation. So, given this graph, can you write the equation that represents the graph? So remember, we can start with our model, y equals ax. This is direct variation. How do we know that? Yes, it has a y-intercept at 0, right? So the only thing we need to complete this graph is the a, which we know is slope, right? So if we start at the point of origin, where we know this graph crosses, right? And we go to this next known point, 2, 3. What is the rise and what is the run? So it looks like we rise 3 and we run 2. Notice we're going left to right. So our slope equals 3 over 2. So now all we have to do is substitute that into the equation, and we can say y equals 3 halves x. And there we've done it. We've written the equation. Now the follow-up to that is, after writing the equation, can you find the value of y when x equals 14? So what will we do? Plug it in, right? Just plug the 14 into the known equation. Y equals 3 halves times 14. Okay. And what do you find when you multiply here? You can reduce, and y equals 21. So when x is 14, y is 21. Awesome. Here's a similar question, but now we do not see the graph of this equation. So go ahead and pause the video, take it down. Could we graph this equation? Yes, we could, because we know that this is a direct variation equation. So if it is a direct variation equation, what is the y-intercept? It is 0, 0, right? 0, 0. Or we could say b equals 0. And so we actually know 2 points, don't we? We know 0, 0, and we know 4, 6. So could we find slope? Absolutely we can, right? We can use our slope formula. y2 minus y1 over x2 minus x1. So let's go ahead and plug in 4, 6 as our second point. So 6 minus 0 over 4 minus 0, right? Look at that. The slope is simply the known point. Because direct variation equations always go through 0, 0, when you know a point on the line, you simply put the rise, the y, over the run, right? The x. And then you can simplify. 6 over 4 is that same slope we just worked with, 3 over 2. Okay? So we know the model for direct variation is y equals ax, and we know the slope, or we can call that a, can't we? So y equals 3 halves x. Now, the second question was, what if x equals 24? Right? What is the value of y? All you have to do is plug it in, right? Y equals 3 halves times 24. And when you do, 2 goes into 24, right? 12 times, and y equals 36. Very good. So we can write a direct variation equation just by finding slope, which is also known as the constant of variation. All right, the final question, or the final example today, is a multi-step problem, just a real-world problem that involves direct variation, right? So pause and take this down. An object weighing 100 pounds on Earth weighs just 6 pounds on Pluto. Assume the weight P on Pluto varies directly with the weight E on Earth. Write a direct variation equation that relates P and E. So the second you hear write a direct variation equation, you're going to go jot down our model, y equals ax, right? Now the difference between our model and this equation is they want us to relate P and E. So rather than relating x and y, we're going to relate P and E. We can do that either by placing, either way, we can call y, P, equals A times E. We could also switch those two. Both of them would reflect this, this real-world problem. But if we write it like this, the weight on Pluto equals something times the weight on Earth, how will we find A? Well, we know here that 100 pounds on Earth, when Earth equals 100 pounds, what is that object weigh on Pluto? 6 pounds on Pluto. So we actually have a known point. And all we have to do now is substitute that known point in this equation. So we can say 6 equals A times 100, right? And now to find A, Simply divide both sides by 100. And we have a fraction that we can reduce, right? 6 over 100 equals 3 over 50. There is a constant of variation, so we can now plug that back in our equation. Pluto's weight equals 3/50 of times the weight on Earth. Okay? The follow-up question would be, what would a boulder weighing 750 pounds on Earth weigh on Pluto? So we simply take our equation that we made and we substitute what we know, 750 pounds on Earth. So we can plug that in for the Earth weight. Okay? And how many times does 50 go into 750? 14 times. Wow, that's a lot. And 14 times 3 would be 42 pounds. Is that incredible? That's not much, is it? 42 pounds on Pluto actually weighs 750 pounds on Earth. Amazing. Okay, there you go. Have fun.